right, so welcome. We started talking about the chain rule yesterday. I just introduced the idea because, and we'll just go back here, mostly to remind myself what I said and didn't say. But the chain rule is whenever you have a composite function. So if you have a function inside another function, or what we'll see later is if you have a function inside a function inside a function, right, then we need to use the chain rule. So we need the chain rule to differentiate these things. Okay. Ooh. I did step 1 of the differentiation, I guess. Identify them, and then I just said, here's the chain rule. Okay. So let's just take it from the top. But I will just kind of jump right in there. I know it's easier to read when it's thin, but I have a hard time writing with the really thin.
I assume you had a very productive Thursday, because I just booted up WebAssign and just to double check, and I'm seeing what I assume is everything else you have to do.
I know, right? But on the plus side, those are all the assignments for the term. But I was like, but I do, so I do go through them and delete questions that I don't like. But what I've noticed is that sometimes, so WebAssign is really stupid. Whenever you do something, you have to tell it to save it, as if I'm gonna delete questions and then not wanna save it. But anyways, so sometimes I still forget to hit save. So, but I know like sometimes Carly will text me and she'll be like, hey, this is a really weird question. I'm like, yeah, that was supposed to be deleted. So I do go through them and delete them, and I've checked up to 3.3 so far, just because that's where the quiz is going up to. So I'll make them smaller, or like try to make them a little bit smaller as we go. But those are all the assignments that we're going to need to do. So that feels good, right? And I'll shift the due dates. I can't remember when I made the due dates, but I'll kind of bump them as we go if they're looking weird. But, okay, so let's just get right into it. 3.4 is the chain rule. And like I said earlier, the chain rule is really, really important. It's whenever we have a composite function, right? So going back to pre-calculus or kind of grade 12, if you've stuffed a function inside another function, then you have a composite function. So if we just take a minute to consider that function that's in the handout, capital F of x is the root of x squared plus 1. Here, right, this, well, first of all, I can rewrite that square root as x squared plus 1 to the power of 1/2, right? That'll be useful because, well, I know how to take derivatives of powers, right? Just bring it downstairs, decrease that power by 1, making it negative 1/2. And so, but now I don't just have x inside, right? So that's what's changed. Now I have a function inside a function, right? And so here I've got a function inside another function. Okay. So we see that capital F of x is a composite function. A composite function where we can let some lowercase f of x, so where we could let, lowercase f of x be the root of x and g of x, right? Just kind of breaking this thing down, x squared plus 1. Okay. So then I could rewrite f of x as f composed with g of x, right? Or if you prefer, I prefer, just because I have a hard time, I don't really have a hard time, but I find it's easier to read it if I see the g of x inside the f of x. So g of x is now inside f of x, right? But these two are equivalent, even though this reads as f composed with g, right? I unofficially read it as of the little o, right? And so f of g, and then it tells me how to write out the composition. Okay. So to take the derivative of a composite function, oops, or I guess we should say to differentiate, it doesn't matter, to take the derivative of a composite function, we need the chain rule. So I'll bring in the official definition, and then I'll give you that kind of, I don't want to say cheater way, it's true, but kind of the shortcut to memorizing it for me, or what I find helpful, is that it's the derivative of the outside times the derivative of the inside. Implied there is the derivative of the outside evaluated at the inside. But for me, that's just a quick kind of, okay, derivative of the outside times the derivative of the inside is what we need to do. So let's see here, bring this big guy in. So first we have g is getting stuffed into f, so g has to be differentiable at x, and f is differentiable at g of x because that's the input of f. We're just kind of going to ignore that. That's not something that we need to worry about, right? The domains of composite functions, not quite yet, at least. So then the composite function f composed with g is differentiable at x if we do this, right? So the derivative of the outside evaluated at the inside times the derivative of the outside. So I'm going to write that down again. And you can use Leibniz notation or these differential operators, but I find it really confusing. So I prefer to just think about it in terms of the prime notation. So let's talk about f prime of x is f prime at g of x times g prime of x. Okay, so this first part is the derivative of the outside evaluated at the inside, meaning the inside you just hold steady. It doesn't do anything. You just take the derivative of the outside, the wraparound function. So derivative of the outside evaluated at the inside function. And then the second part is times the derivative of the outside, or sorry, of the inside. Oh, does make sense? Times the derivative of the inside. Okay. So to help me remember, and this is just me personally, to help me remember, I would almost say chant. I say the derivative of the inside, or sorry, mess it up again, of the outside times the derivative of the inside. And then it's understood that the derivative of the outside is evaluated at the inside. But that just kind of helps me keep them straight. So of course, you have to figure out what your outside function is and what your inside function is. And we will see examples where we've got more than two functions being stuffed inside, right? And so we'll look at how to deal with that. But really, you just keep chipping away from the outside, right? But let's do, let us do an example first. So let's actually find this derivative. I gotta mark this up. There. So let's actually find this derivative. Okay. Now, it doesn't matter if you want to find the derivatives of the inside and the outside kind of independently, but for me, I just jump right into it because you're doing the derivative of the outside evaluated at the inside, and then so that way you can kind of break them up. So first thing we're going to do is we're going to say, well, f of x is really x squared plus 1 to the 1/2, right? We're always going to want to change our roots to powers, right? So powers of 1 over n for the nth root. So now, taking the derivative of the outside means just ignoring x squared plus 1, treating it as if it's one thing. Okay? So then I can bring that 1/2 down in front. So I get f prime of x is 1/2, and then x squared plus 1 stays inside to the power of 1/2 minus 1, just to kind of emphasize that that's where the negative 1/2 is coming from later. So this is the derivative of the outside. Derivative of the outside. Okay. And then we're going to multiply by the derivative of the inside. But notice that this is also kind of I almost said cheap derivative, kind of like a quick and easy derivative here. X squared plus 1 is just going to be 2x. So here times 2x. Technically plus 0 if you want. You don't have to. I just wanted to show you where the 1 went. So this is times the derivative of the inside. So we can simplify this, right, a little bit. The power of negative 1/2 is going to bump that x squared plus 1 square rooted down to the denominator. So here, this is going to become 1 over 2 root x squared plus 1, right, times 2x. But this 2 up here and this 2 are going to cancel out. So I'm left with, this is x over the root of x squared plus 1. I have pretty fond memories of the chain rule. So I used to have math parties. And so with the math department, and we would have derivative offs. So someone grabs the Calc 1 textbook, and then you just yell out a derivative, and then there was drinking involved. So yeah, it was pretty fun.
That actually does sound fun.
Yeah, so you'd have derivative offs, and like various level masters and PhDs in math kind of having derivative offs. And one of my friends, she's so competitive. She yells, "Done!" And then our moderator was this really kind of timid girl, and she goes, "You forgot the chain rule." And so my other friend goes, "Where?" She's like, "Everywhere." So chain rule for me, that's a really funny memory that I have. So don't forget the chain rule, especially if you're in a derivative off. So it makes a big difference. So I have to tell that story because I think it's really, really funny. All right, so of course, because we're taking the derivative of the outside and then the derivative of the inside, the other rules will be incorporated, right? So as we are taking the derivative of both the inside and the outside, or maybe I should say them in the order that we do them, of both the outside and the inside, we will often need to combine the chain rule with other differentiation rules, right? Things like the power rule, the quotient rule, the product rule, right? So all those rules, like we just did with the polynomial x squared plus 1, right? We know how to differentiate a polynomial now easily, right? But we might have to incorporate kind of big things like the quotient rule or the product rule. Okay, so just kind of keep an eye out for that. So as we're taking the derivative of both the outside and the inside, we will often need to make use of other differentiation rules, right? So the product or quotient rule, for example. Inside the chain rule, or I should say along with the chain rule. Along with the chain rule. So in the notes, I did include the chain rule along with the power rule, or the power rule, which is what we just used, right? And so here, if we let u be g of x, so that's something that we're going to do maybe later on, definitely in Calc 2, where you make these substitutions, right? And so in fact, it's called a u substitution because that's our go-to substitution. So then we say, okay, instead of talking about g of x as a whole thing, in example 1, we would have let u be x squared plus 1, right? Because then we have u to the 1/2. I can differentiate u, but then I also need to multiply it by the derivative of u. So that is the chain rule. So here, if I let u be g of x, then if you have u to the power of n, then of course it's just the power rule that you're applying here. So you don't really need this blurb as long as you understand the chain rule in general, right? But then the power rule is going to come into play quite a bit. And so let's see here if we can handle example 3. Maybe I can squeeze it in here. So if I want to differentiate y equals x to the 3 minus 1 all to the power of 100, right? So now we're going to kind of start training our eye to say, okay, do I have a function inside another function? Yes, I do. So then we need to apply the chain rule. So then, and I'm going to try to keep it on the same page. So this becomes y prime is 100 times x to the 3 minus 1 to the power of 99, right? 100 minus 1. But then you don't want to forget about the derivative of the inside, right? Times 3x squared. And then I'm not going to keep writing the plus 0 or minus 0 in this case because it's redundant. We don't need it, right? So it's times 3x squared. So we can simplify that a tiny bit, right? 3 times 100 it should be 100 minus 1, so 99. I didn't show very much work. And that's okay. We can start kind of just, awesome. We can just start doing that, right? Just decreasing by 1. Sometimes if I'm dealing with a fraction, so if I have something like 3 over 5, then maybe I'll do minus 1, just so I can, that's more for me to visualize it, because then I need a common denominator, right? And so I need to kind of see it to get there. But if it's something like this, you can just jump to it. So 3 times 100 puts me at 300, and then x squared times x to the 3 minus 1 to the 99. X to the 3 minus 1 to the power of 99. There's no way that I'm going to expand that out. That's x to the 3 minus 1 times itself 99 times. No, thank you. So I'm just going to leave it there. Maple would do it for you, but it still wouldn't be nice. So we'll just leave it like that. Okay. Good. So let's do another example. So these, I guess I can just grab them like that. So these problems also kind of get us to practice rewriting a function as a polynomial, right? And so if you have a root in the denominator, well, you can just bring it upstairs by making it a negative power. So here, right? And so those are tricks that we learned way back in 3.1 when we were first kind of introducing how can I manipulate this in order to make it look like a polynomial, right? Here it's a little bit more than a polynomial, but same idea. So if we rewrite f of x first, right, 1 over the third root of x squared plus x plus 1, it should be pretty obvious. I hate to say obvious in this course. Nothing is obvious when you're first seeing it, right? But it should be, kind of jumping out at you that you've got x squared plus x plus 1, which is its own function, inside 1 over the third root of that, right? And so this we can rewrite as x squared plus x plus 1 to the negative 1 over 3. Oops, can't. There. Make sure you make that negative, right, to bring it up to the numerator so that you can deal with it just as a power. Okay, so now this is definitely one of those cases where I am going to show the subtraction of 1 in my derivative. So here I've got f prime of x is negative 1 over 3. That's fine. The inside just stays the same, right? So I can just write that down. X squared plus x plus 1 to the negative 1 over 3 minus, instead of 1, I'm just going to rewrite it as 3 over 3 right away, because I need to have a common denominator. So minus 3 over 3. Okay. And then you don't want to forget about the derivative of the inside. So then we're going to multiply by the derivative of the inside, which is 2x plus 1. So individually, right, these derivatives are not hard. It's just combining them with the chain rule that is the new thing. So I can simplify this a little bit, right? I've got -1 minus 3, putting me on -4 over 3. Okay. I might have to take my time kind of simplifying this here. So a -1 over 3 times x squared plus x plus 1 to the -4 over 3 times 2x plus 1. The 4 over 3, right, ignoring the negative for a quick second, the negative just bumps it down to the denominator, right? But the 4 over 3 means the 4 stays on the x squared plus x plus 1, and then I'm taking the third root of that. So this becomes 2x plus 1 over 3 times the third root of x squared plus x plus 1 to the power of 4, and that root is like that, all over that x squared plus x plus 1 to the power of 4. And that's just going back to our exponent laws, right? And it's been a while, I would say, that since we use them and practice them, so maybe just do a little refresher. Okay, if it's not clear.
Quick question.
Hit me.
The negative in front of the -1/3, would that make the entire thing negative?
Yeah, so this one that I forgot.
Yeah, that one.
Yes, it does. Good catch. What a mess that would have made. Hey, you guys are on the ball. That's awesome. Good, good, good. Yeah. Just the negative hanging out in front. All right. Ready to level up? Let's do example 5. Okay. Leveling up indeed. So now, right here, I have the quotient rule inside here. I don't see any way that I'm going to be able to simplify and cancel anything here. So I'm stuck with the quotient rule. That's okay. I know how to use the quotient rule for something like this, right? So that's not bad. It's just the first time that we're seeing something other than a polynomial inside. But then we still have a power rule outside. Okay, so here we've got quotient on the inside. Oops. And by that I mean a quotient rule. And then on the outside we have a power rule. You can write g prime of t if you want. It's just of t, right? Because the t is the variable inside. What I will do is I'm going to use d dt notation just because I want you to see it so it's not so bad, right? So we're not just using prime notation, even though it is a lot easier to read. So then d dt, meaning I'm differentiating with respect to t, right, because that's my variable, of g of t is the derivative of the outside evaluated at the inside. So that's going to be 9 times t minus 2 over 2t plus 1 to the power of 8. Right, so that just kind of holds steady here. So this is the outside. And then now I need to apply the quotient rule. But before I do that, I'm just going to emphasize that I'm going to take the derivative of t minus 2 over 2t plus 1. Right, so here it becomes d dt. So times d dt of t minus 2 over 2t plus 1. Right, so here, just kind of match it. This is the derivative of the inside. We haven't found it yet, but we will. So there's the outside is kind of dealt with, right? So now I'm going to focus my attention on taking the derivative of the inside, making sure that you're multiplying the derivative of the outside by all of it, right? So big square brackets probably are your way to go here. And maybe I'll switch up my brackets here. So I have 9 times t minus 2 over 2t plus 1. Nothing's changed here. No, you don't need to use ddx. In fact, I'm pretty sure it just wants the derivative, so it'll just say what it is outside, and then so like ddx equals, and then you just tell it what the derivative is. So no, you don't have to use the ddx. Yeah. No one likes it. Okay. So now times the derivative of the inside, which itself is, I know, for me, the differential operators, I hated them. They didn't make sense to me. I just would kind of seize up when I saw them. And that's totally, I hope normal if you feel like that, because that's how I felt. But it is good to kind of see it and just kind of normalize it a little bit. So, but I totally get that they are confusing. Because that was me too. Okay, so I've got the quotient rule. So maybe just as a reminder, and hopefully you have some sort of cheat sheet that's available kind of close by, where you have the quotient rule, right? But so the quotient rule was what? The derivative of the first times the second minus the first times the derivative of the second over g squared. Right? So the first in, oops, not in pointer mode. The first in this case is t minus 2. So the derivative of that is just 1. And then the derivative of the g here is just going to be 2. So now I'm going to kind of compose my quotient rule here. So I've got 1 times 2t plus 1 minus t minus 2 times 2 all over 2t plus 1, and then don't forget that square. And we'll just kind of draw a little arrow to the quotient rule because that's what we're using here. So I can expand this a little bit and just kind of simplify, especially seeing 2t plus 1 and 2t plus 1 over here. Right here, it's to the power of 8, and here it's to the power of 2. So we can probably combine those, but let's, oh, sorry.
Okay, so I just want to double check that the way I've written it out makes sense.
Okay.
I'm sorry for the poor camera quality.
No worries. Okay, so let's see here.
Just realized it's mirrored.
Oh, yeah, I wasn't.
Half a second.
No worries.
How do I get this to unmirror? It's probably under
That I
set.
have no idea.
Probably under settings somewhere. Give me a quick second, because I want to make sure that I'm not going about this oddly.
Totally.
Video.
No, it's
Mirror. There we go. All right, now.
okay, so we've got 9, and then
Okay, that's, yeah, the quality. Yep. So we have 9. That's just the regular
Yep.
FT and GT. And then
Yep.
it's GT times F or F prime T minus all
Yep.
that jazz.
and then all of a sudden you switch to X's. It doesn't matter as long as you keep them straight, right?
I did swap to X's because
That's okay.
I am
It
so
happens
used to it.
because we're so used to X's.
Mhm.
But no, that looks good.
All right, so that is a way to go about that, if it might be a bit long.
Yeah.
I'm mirroring my.
Well, I mean, yeah, it's
There
proper.
we go.
I know T's are so weird. We're so used to X's.
All right, so that is not an incorrect way of going about things. Good.
It is not. In fact, it is correct. But you don't want to forget about your power of 8. I couldn't see if you had your power of 8 on the outside. Oh yeah,
I had missed it, so thank you.
Yeah, so that's why I started writing my T's, or I've always kind of written my T's like this with a little curve, so that, because otherwise my T's look like pluses, exactly. And kind of same deal with how I write my X's. They've got kind of like a flourish to make them not look like multiplication X's. Yeah, you gotta add a little pizzazz. So now let's see if we can simplify the numerator here, because now we're done taking the derivatives, right? Now it's just a matter of simplifying as much as we can. So now for the fun part, 9 times, and you know what, just to emphasize that these are the same, I'm going to do t minus 2 to the power of 8 over 2t plus 1 to the power of 8, right? The exponent laws say that I can bring in that power of 8 onto both the numerator and the denominator, as long as it's wrapping up the whole thing. And then times 2t plus 1 minus 2t plus 4, right? Just expanding out that numerator over 2t plus 1 squared. Cool, okay. So now I see that I'll be able to combine these because I have the same base, 2t plus 1, right? And then if I'm combining bases, the same base, then what do? I have to add my exponents, right? And so, and I also see something nice. I see that 2t is going to cancel with 2t, so haha. And then 1 plus 4, even I can do that, should be 5. Which I will later multiply by 9. Actually, let's just go for it. 9 times 5 is 45 times t minus 2 to the power of 8. I wasn't able to get rid of anything there. And then that's all to the power of 2t plus 1 to the power of 10. Aha. We did it. Chain rule with something other than just power rules inside. Okay, let's do another one. Product rule, maybe. I think it's the product. Oh, I see. Let's do example 6. Okay.
Quick question.
Yeah.
I noticed another slight slip up. Actually, no, wait, correction, 45 is in fact 9 times 5. I lost
My
track.
9 times
Cool.
tables are rusty, but I'm feeling pretty confident.
All right, yeah. I thought it was
Mostly
like
because
4.
I
thought
recalculated.
I saw 9, then 4, glassed over
Mm,
the 1, saw the 45, looked at mine, saw 5, and then there was a bit of a disconnect somewhere.
no worries. No worries at all. Okay. This is a mumbo jumbo, huh? So here, what are we seeing? Well, I see the product of two things, but those two things require the chain rule, each of them. Oof. Right, so let's see here. So here I've got the chain rule. Chain, chain, chain. What is it? Chain of Fools? Is that the song?
Not
And then
ringing
I've
any
got a
bells.
chain. Pardon? No idea. Oh, the 45 came from, so 1, I skipped a step. 1 plus 4 is 5, right? And then 5 is going to multiply by the 9 when I simplify. So 9 times 5 is 45. Nice. So now I've got a chain rule times a chain rule. So outside here, I have a product rule. Things just got real. We just need to, and I shouldn't say just, we need to just kind of go through it really slowly and methodically, right? Because I know how to deal with the chain rule, and then I know how to deal with the product rule, but then that product rule, when I'm taking the derivatives of the first or the second, also involve the chain rule. So I need to kind of keep my head on straight here and be really careful. You can use prime notation, but I will use ddx notation just because whenever I'm showing that, hey, here's a derivative, it's nicer to have the ddx notation than the prime notation. Okay, because the prime can look like a power of 1, which is ignorable, right? And then you might miss it. And technically we should use ddx. So again, ddx of y, or if you prefer dy dx, that's fine. First, I need to deal with the product rule, right? And so that's going to be, so the product rule, remember, is f prime g plus f g prime. And I use that same order, but just with addition as I did in the quotient rule. So for me, that helps me remember, because I want to have all these memorized. So whatever you got to do to kind of tweak it a little bit. So I find that that's helpful. So the derivative of the first, okay, I'm going to indicate by saying, okay, I'll use big square brackets around each of these. D dx of 2x plus 1 to the power of 5 times g held steady is just times x to the 3 minus x plus 1 to the power of 4 plus, okay, now the f is being held steady, so 2x plus 1 to the power of 5. And then the derivative of g is, I'm just going to rewrite it here, d dx of x to the 3 minus x plus 1 to the 4. Right? So here I've written out the product rule. And then now each of these will require the chain rule as well. Making sure that each of these chains are all being multiplied by these little guys outside. We really leveled up here. Okay. So now I'm going to keep those big square brackets just to make sure that everything is being multiplied as it should be. So I want to take the derivative of the outside. Okay. So I get 5 times 2x plus 1 to the power of 4 times the derivative of 2x plus 1 is just 2. Okay. So this is the first chain rule complete. Right. And then I need to multiply by x to the 3 minus x plus 1 to the 4 plus 2x plus 1. These are just, nothing's happening here. I don't need to find any derivatives. But now I need to find the second chain rule, which is going to be the outside 4 times x to the 3 minus x plus 1 to the power of 3 times 3x minus 1. The derivative of the inside. Sorry, 3x squared. I have a feeling you guys would have caught it. Pretty sure I made that same mistake when I wrote out my notes before. Something for myself to keep an eye out for. Sloppy. Okay, now we're done differentiating, right? So the hard part is over. Now it's a matter of simplifying. I'm seeing some common multiples that I'll be able to use. And so here I'm seeing a common multiple of, let's see here, 2x plus 1 to the power of, well, definitely 4, because I can grab 4 from here, leaving 1. So here I have those guys. I can pull out a common multiple. And let's see here, 2, 5 and 2, but I only have 4 over here. So I can pull out a common 2. And then last but not least, I also have an x to the 3 minus x plus 1 over here on the first lump. I have 4 of them. And over here, I only have 3 of them. So I have a common 3. So here, or maybe we find that we have a common 2, writing out the constant first, times 2x plus 1 to the 4 times x to the 3 minus x plus 1 to the 3. Right. There's a lot of common factors here, so you want to keep those straight. So I'm going to write those. I'm going to pull those all out to the front, making sure I kind of keep track of where I have more and where I've pulled out all of them. So 2 times 2x plus 1 to the 4 times x to the 3 minus x plus 1 to the 3, then times 5 times x to the 3 minus x plus 1, because I only had a common 3, but here I have 4. And then I pulled out 4 of these 5, so then plus 2x plus 1 times 2. I'm going to bump that 2 out front here. Like that. Okay, 2x plus 1 times 2. And then I used up all these x to the 3 minus x plus 1 to the 3. Okay, so the only thing that's left is the 3x squared minus 1. So times 3x squared minus 1. What I'm seeing is I'm seeing an x to the 3 and then an x, and then I have an x, which is going to expand to x to the 3. So I see that I'll be able to kind of simplify this a little bit. All the while, these common factors are just going to hang out outside, right? We still have to write them down, but right, so now we can simplify here. Right, so simplify. So you get 2 times 2x plus 1 to the 4 times x to the 3 minus x plus 1 to the 3. Just writing out that common factor. Then I'm going to expand all these out. So I get 5x to the 3 minus 5x plus 5. And then do I dare try to expand these all in one go? Right, expand the 2 onto the 2x plus 1, so that makes 4x plus 2, and then expand that onto the 3x squared minus 1. I think I can do it mostly to get this question over with. 4x times 3x squared puts me at plus 12x to the 3. 4x times negative 1 minus 4x. 2 times 3x squared is plus 6x squared, and then 2 times negative 1 is negative 2. I see common factors galore here. And so, all right, let's do it. 2 times 2x plus 1. That's the common factors just stay the same, right? All this simplification makes you appreciate that the derivative itself wasn't actually that bad. It's the simplification here that's bad. Not bad, tedious. Expanding. Make sure you check your negatives, all that stuff. So 5x to the 3 plus 12x to the 3. 5 and 2 makes 7, so 17x to the 3. I'm going to cross these off as I grab them just because otherwise I'll get confused. Plus, I think I only have 6x squared. Then I have minus 5x minus 4x, putting me at negative minus 9x. And then 5 minus 2 plus 3. We did it there. I don't see anything else that I could simplify. So now we just leave it. I'll even put a smiley face because man, oh man. Let's do example 7. Unless any questions about that one? That's a big one.
Yeah, kind of lost me halfway through. Ooh, but that's also because I'm trying to figure out a way that I can write this down without losing track of things.
That's the key, isn't it? Trying to sort things out. Yeah, so you really want to kind of just kind of stay focused and work through it methodically. Otherwise, you will get tripped up. But also another key thing would be to pull out these common factors, because if you don't do it here at the very beginning, it's going to be just a complete nightmare to see like what your common factors are. So that's something too. But yeah, so pretty big, but the derivative itself isn't bad, right? It's the sorting things out that's bad. Let's do one that's not bad. It is trig functions. Do you mean like this example here? So if there's a bracket showing an obvious inside and outside function, then what do you do? No, I think I prefer BS instead of ES. Do you have one in particular from WebAssign? Because then we could. 7 was the first one I saw. Let me just go there and maybe try the y equals e to the sine x. Try that one while I go. Is it from the, let me just sign in here. Sorry, I can't see the chat. Okay, so from 3.4, 7, 11, or 8. Let me just go there. I'll check out 7 first. Okay, so I'm just going to jot it down. Let's do this one because this one's actually going to help us a little bit on the way. But so WebAssign question 7. For me, I have g of theta equals 3 cos to the 4 of theta. So we will do that one after this one. Okay. All right. So let's do this example 7 first. So we've got y equals e to the sine x. So I've got sine x inside of e to the x, right? And so my my inside function is sine x, and my outside function is e to the x. Now we remember that e to the x, or e to the anything, is just the derivative of e to the anything is itself. But now that we have a power of something other than x, we need to use the chain rule. So if in y equals e to the sine x, right here, this is my inside. And then my outside is e to the x, but then evaluated at sine x, right? And so here, when I take the derivative, I need to remember that y prime, well, e to the x is just e to the x, right? That's what's nice about e to the x and pretty cool about e to the x. So e to the x evaluated at the inside, so e to the sine x, that stays the same, right? So, and I think, Carly, you'd asked last day, right, is it always just itself? And then I said, not yet, we need the chain rule, right? Because sometimes we'll need to multiply by the derivative of the inside, right? And so now I need to multiply by, and you're not gonna like this, d dx of sine x, which is the derivative of sine x. Remember, only the co-functions are negative. So I know that sine, the derivative of sine is cosine and the derivative of cosine is sine, right? I know they have that relationship, but it's the derivative of cosine is negative sine, right? So whatever you need to do to kind of remember those or have them available on a sheet somewhere, then you'll be off to the races. E to the sine x cos x. Done and dusted. So now I'm going to grab maybe I'll clean this up here. Web assigned 3.4, question 7. And I'll write it a little bit nicer here. G of theta, only a little bit nicer. 3 times the cos to the power of 4 of theta. I actually have this. This is really good to go through this one here because I actually had to add an example just so that we could see and remember that if I have cos to the 4, I can rewrite that as cos of theta to the power of 4. Right? So this is the same as 3 times the cos of theta to the power of 4. So now it's a little bit more obvious that the cos of theta is on the inside and then the outside function is x to the power of 4, right? Evaluated at the cosine of theta. So now what I get is remember the constant outside, we just kind of hold it there. It's going to multiply this 4 when I bring it down, but we don't need to take the derivative or anything. We can just bump inside onto the cos or the cos theta to the power of 4. So g prime of theta becomes 3 times 4 times cos theta to the power of 3 times negative sine theta. Right, cos theta, the derivative of cos theta is negative sine theta. Putting me at what? Negative 12 cos, and I'm going to write it the way that they wrote it, cos to the power of 3 theta. Or if you want to have cos theta to the power of 3, it should accept that too. But usually we write it like that. Cos to the 3 theta sine theta, because I moved that negative out front already. Let me just see how they wrote. Yeah, so they did do the cos to the 3 theta instead of cos theta to the power of 3. Does that kind of make sense? So sometimes you have to dig a little bit for kind of the outside versus inside function, sorry, BS inside function. But they're there. this is all a lot harder too, right? When you, on the test or on a quiz, for example, when we've got all these rules mixed together and you need to recognize the chain rule, that's harder than knowing, okay, this is my chain rule section. All of these are going to use the chain rule, right? Try it. Let me see if I can. I don't think I can try it on this page that I'm at. It should know that cos theta to the power of 3 is the same, so it should be okay with that, but only one way to find out. Okay. So it should be okay with it, but if it's not, then you know to change it. All right. Oh, I forgot to give you guys a break. Do you guys want a break or do you want to end a little bit early today? Decisions.
I'm thinking I'm good to continue. I don't know about the others.
Let's just keep going then. Let's do it. We're on a roll, crushing WebAssign. Let's do it, and then we'll end early. Okay, good. Yeah, so that'll be kind of something that you'll need to do. Let me just have a look at question 8, because I think you said 8 and 11. Oh yeah, so 8 is very similar to this one that we just did, right? So it's e to the power of a polynomial instead of sine x. So then e to the x is the outside function. And then let me see 11 here. Oof. Okay, well, we haven't done 11 yet, so let's save that one because we'll need blocks. Yeah. So let's talk about logs first. To differentiate exponential functions, so exponential functions are functions where the x is in the power, right? So to differentiate, an exponential function, which is that question on WebAssign that we will go back to. I do want to go through that one because it looks pretty fun, but we need to learn some stuff first. So to differentiate an exponential function, we use the chain rule. It is assuming that the base is positive. I think that's, you don't think that sounds fun? Oh. It looks fun. It looks so juicy. It's huge. So I think we get trained to see these hard problems, and then the satisfaction of being able to solve it eventually, that's what makes it fun. Yes, good. Hopefully I'm able to solve it on the fly here. So to differentiate an exponential function, and I just want to make a note here that an exponential function is something. Exponential function is if you have b to the power of x, whereas a power function, right? The power function If you have a power function, then we can just use the power rule, which was the first rule that we started with, right? Where you just bring the power downstairs and decrease it by 1, right? So the power function is where x is down here in the base, but now we're talking about exponential functions where you have x in the power, exponential function. So let's see here. We need this little guy, this definition here. And I kept a little there. So what we find is that the derivative of b to the x becomes b to the x times the log of b, and of course I say the log, but it's the natural log, but that's the only log that we'll use, so we can just call it the log. So b to the x times the log of b. So that's where it gets a little bit weird, right? So we need to see, where did this come from? So kind of, I don't do a lot of proofs with you guys because I find that they can get really bogged down, and it's not something that I expect you to do, but there will be a few times. So this is one of those times where I want to walk you through the proof and show you where things came from. And then when we find the derivatives of inverse trig functions in the next section, I'm going to do a proof of that as well, just to show you where things came from. Otherwise, it is fine to just go ahead and use it blindly, right? But here's why. So first thing we need to do is we need to rewrite b to the x as an exponential function, e. So we need to rewrite b to the x. So b to the x becomes e to the log b of x. One thing that I want you to remember is e to the log of b is just b, right? So I've kept it, and so this is the key to this proof, is rewriting this b as e to the log of b, and then times x. If I take the derivative of this thing, so now I'm taking d dx of b to the x is the same as d dx of e to the log bx. Up here in the power, you need to remember that the log of b is just a number, right? So it's a constant. So really, I just have e to the power of a constant times x, right? So if I'm differentiating with respect to x, then it's just going to be that constant. So here, remember, log b is just a constant, right? It's just a number. We don't know what it is, but it's just a constant. So if I have e to the power of something to the inside, well, when I take the derivative of the outside, I get just e to the log of b times x, right? Derivative of the outside times the derivative of the inside. Derivative of the inside, d dx of the log b of x, or log b times x, is just log b. So it becomes log b. But another thing that I wanted to point out here is this e to the log b of x, I'm going to convert it back to b to the power of x. Yeah. So this becomes b to the power of x, right? E to the log b times x is just b to the power of x. So then I get b to the power of x times log b once I take the derivative of log bx. And I'm going to bump it up so it's on the same page here. There. All right, so that's where this came from, and I'll do a little end of proof box here. QED. Can't remember what QED stands for. It's like end of proof. I'll have to look it up. All right. Or I usually just use a little square. So that's where this is coming from. So now we can just go ahead and just blindly use it, right? But the hard part is going to be to recognize, okay, now I have an exponential function, so I need to use this special derivative, right? That's the hard part. So let me see here. We'll just jump right to it. WebAssign 3.4 question 11. Let me see if I can jot it down here. Why is, so in my case, and we might have different numbers, but is 3 to the power of 4 to the power of 5 to the power of x. Okay, can do it, can do it. Make sure I don't flub this. Oh yeah, so Carly says she has 5, 6, 7. Doesn't matter. So I'll do it with 3, 4, 5, and then you can have kind of a little crutch to do your own numbers. All right. Yeah. Yeah, they must have told it that it should be increasing even, or maybe that's just a fluke. Yeah, 3, 4, 5 versus 5, 6, 7. Wonder if someone has 7, 8, 9. All right. All right. So, here we go. I'm stalling, I guess. All right. First, we need to figure out what the inside and the outside functions are. So, what can I do? I can do, what is my inside function and what is my outside function? I'm gonna do this whole thing, 3 to the 4 to the 5, as my inside function to the x. Okay, so I am just going to try it. I don't know exactly how to do it. Okay, here we go. So I'm going to rewrite this as 3 to the 4 to the 5 to the power of x. Okay, and we just established that it's going to be, and I'm going to copy this down here, copy. Okay. So now my b is going to be 3 to the 4 to the 5. Okay. Let's see here. So d dx of y is going to be 3 to the 4 to the 5 b to the x times the log of 3 to the 4 to the 5. I'm just using up to two lines just to emphasize that it's 3 to the 4 to the 5. Okay. I have log laws. I'm going to cheat here. 3 to the 4 to the 5. Okay. And then, all right. But what happens times the derivative of the inside? I feel like this would be one of those ones that I would delete. Now we're doing it. The derivative of the inside is just a constant. So that's the hard part, or that's what I'm having a hard time with. What if I start because then I want to multiply by the derivative of the inside, but that's just going to be a constant, right? So that's what is tripping me up here. Okay, so I'm going to backtrack here. I'm going to delete this because it wasn't working. Maybe I'll use 5 to the x as my inside function. What happens? 5 to the x gets brought down. I am cheating. Okay. What if I rewrite it like y equals 3 to the 4 to the power of 5 over x? Okay. Then the derivative of y becomes, so now just kind of treating 3 to the 4 as a constant, which it is, to the power of 5 to the power of x. But then I have -1. I'm ready to delete this question, or at least maybe take some time alone, quiet, to work through it, because I don't want to keep leading you down the wrong path. But this would become, so here's where I hesitate, is because then I would bring my 5 to the x downstairs times 3 to the power of 4 to the power of 5 to the x minus 1. I'm just not sure that that works, that is legal math. So that's why I'm kind of pushing the brakes here. I don't really want to do that. So I'm ready to do this. Stay tuned. Yeah, that's fair. So you're confused, totally fine. Me too. I'll give you guys the answer so that if you're trying it, then you can kind of see what you get to. So here, the answer that they have for this one is y prime is the log of 3 times the log of 4 times the log of 5. I think I just need a little bit of time to kind of just work through it, times 3 to the 4 to the 5 to the x times 4 to the 5 x, not to the power of x, times 5 to the x. I suspect this might actually be a typo. I just, looking at what these things look like, right, it would make sense.
Looking at the answer there, my first instinct is that they start right at the top with 5 to the x as being inside of another thing that's inside of a third thing. So
yeah, right. So that's it. Yeah, so I'm kind of like, okay, but it didn't, I don't know, it didn't pan out. I'm not sure if this could maybe it's supposed to be 4 to the 5 to the x, which would follow the same pattern here, right? Whereas I don't know. Anyways, I'll keep it for a bonus if you want to do it. If you don't want to do it, that's fine. Keeping as bonus. I mean, now that you have the general idea, you could probably just recreate the same answer with your numbers, but I'll keep it as a bonus, but not for marks. I'll stick to my pre-worked examples, thanks. We were already doing it, right? But what I wanted to say next, let's just kind of parking lot that. I'll go through it and have it ready for next day, but oh yeah, so what we can do is we can actually have more than one chain rule. So here, right, we would apply the chain rule more than once, right? And then we kind of chip away from the outside. So here we can extend the chain rule, right? And that's what I was trying to do. I tried it on mine, and it is supposed to be, oh, nice. Yeah, weird, but okay, good. So it is supposed to be 5 to the power of x. Okay. Weird. So we can extend the chain rule to more than 2 functions. And I kind of think of it as by chipping away from the most outside function to the most inside function, from the most outside function to the inside. Okay. And that is why it's called the chain rule. In fact, it has I have a little blurb here. Oops, back to the wrong page. So here, right, the chain rule, if you have, and they use, let u be f of u and u be g of x and x be h of t, but really what we're saying is that if you have f of g of h, right, so here, this is really what it's saying. If you have y equals f of g of h of t, for example. 1, 2, 3. So now I have h of t inside g inside f. So now I apply the chain rule still, and But then I arrive at another chain rule, right? So you just kind of move in from the outside towards the inside. So let's see here. Let us do some trig functions. Another thing I know people don't like trig functions. Me neither, typically. These ones are fine though, because just having a gander here, I see that tan of x is inside of cos of x, but cos of tan of x is inside sine of x. So I have these kind of 3 different functions, but here they're kind of obvious to see, right? So we're just going to chip away at this thing until I'm done with the derivatives, right? So if I take the derivative of the outside, which is the derivative of sine, which is cosine, then if I multiply by the inside, that's the derivative of the cos of tan of x, right? So that's another chain rule. So that's why it's the chain rule, because we keep just kind of building stuff on. So if we have f of x, which is sine of cos of tan x, making sure you have those derivatives of trig functions kind of handy somewhere. So here we've got this outside function of sine, and then we've got this inside function, also a chain. Right, so also a chain rule. Okay. So I'm going to take the derivative of the outside, evaluate it at the inside. So this becomes the cosine of tan x times the derivative of the inside, which I will just highlight is the derivative of cos of tan x Now applying that, I get the cos of tan x times the derivative of cosine is negative sine. Negative sine evaluated at tan x times the derivative of tan x, which kind of less memorable, is secant squared x. But definitely, if you just have that little table that I gave you handy somewhere, then it's not so bad. Worse if you have to memorize them. Okay, these are all being multiplied across, right? So first thing I'm going to do to kind of set myself straight is I'm going to bring this negative out front, and then I don't actually see anything else that I can do because I can't simplify the cosine times cosine because it's actually the cosine of tan x. So there's no simplification that I can do. The only thing that I can simplify is moving this negative out front to really emphasize that this is all being multiplied together. So this puts me at the negative cosine of tan x times the sine of tan x times the secant squared of x. And that's it. I want to do this last example, and then you'll be free. Make this a little bit bigger. So if I want to differentiate e to the secant of 3 theta, notice now that I have, well, e is my very, very outside function. And then the inside function is the secant of 3 theta, which is also a function inside, right? 3 theta is its own function. So if I rewrite this, y equals e to the secant, and then I'll emphasize it, of 3 theta, right? So here, this is a function, and this is a function, right? So I have a function inside another function. So if I do d theta of y, or dy d theta, if you prefer, I actually like just having the d theta outside and then times y, or like of y. Or you can do y prime, it's fine. The derivative of e to the anything evaluated at that inside function is just itself, right? So we have e to the secant of 3 theta times the derivative d theta of the inside, which is secant 3 theta. You can just go for it. You don't have to pause and write out the derivative here. But I just want to emphasize that, okay, now I'm taking the derivative of this, also a chain rule. So then I have e to the secant 3 theta times, and the derivative of secant x or theta or whatever is the secant of x times the tan of x. So that is kind of a curveball. Okay. But it's going to be the secant and then evaluated at the inside 3 theta times the tan of 3 theta times d theta of 3 theta, right? Which is just going to put me at 3, which I'll write it out in 2 steps. There's no harm here, but e to the secant of 3 theta times the secant of 3 theta times the tan of 3 theta times 3, or if we bump that 3 out front, it'll make it look a little bit nicer. So we get 3e to the secant 3 theta times the secant of 3 theta times the tan of 3 theta. Another case where I don't actually think that the derivatives themselves are that bad, but when we have to chain them together and do them all together, it gets a little bit hard to focus. Okay. So that is the end of the chain rule. And like I said, I will work through that other problem just to kind of talk you through it quickly next day. But have a look through 3.5. Yeah, exactly. So whenever you have any variable, you can just replace it with x if you want to. Right, but in this case, because it's trig functions, we usually use theta instead, but it doesn't matter. And then we're just taking the derivative with respect to theta instead of with respect to x. So it behaves the exact same way as an x.
I want to say I understood all that. I'm not entirely certain I did.
That's okay. That's okay. It will require some practice, some pretty extreme practice.
In that case, if we're done for today.
We sure are.
If I don't start understanding it over the weekend, you can expect to see me burst into tears on Wednesday.
Well, I hope that doesn't happen. But
Probably not.
Yeah.
But forewarning.
Yeah. And remember, the quiz is closing tonight. But if you do need me to keep it open till Sunday or something, then I can do that.
I'll be able to get it done. I just will need to make sure I do a quick review before taking it.
And it's only up till 3.3.
Mm-hmm.
So not
All right.
the general. All right.
See you Wednesday.
See you Wednesday. Have a great weekend, guys.
I'll try.